the last thing we have to look at is a different transformation that's happened. Right, so we've got here a table of values again from -4 to +4 this time. You might remember the last time the table of values went from 0 out to 9, but this time we've got from -4. Now you might think, oh, if you put -4 in place of x, you can't do anything, so that's a bit silly. And you notice that in the table it's all undefined, which backs up your claim. The green dots then stretch out to the right and show you that you can actually graph that. However, there is another transformation that can happen, and that's a reflection across the y-axis. And the way we show a reflection across the y-axis is to take the square root the same as before, but every x value we take the opposite of. So now, when the x gets plugged in, the first thing that happens is it gets turned into the opposite of it. So -4, the opposite of -4 is +4. And now I can take the square root of +4, which is 2. So you might see here that even though the x input is still negative, the rule has got a special negative sign built into it, which allows the square root to be taken. So -4 input, +2 output. -3 input, +1.7 output. -2 input, +1.4 output. -1 input, +1 input. And you might then notice the symmetry. So the symmetry is across the y-axis. All right, so you can see the points 4, 2, oops, those points there. 4, 2, same as -4, 2. 3, 1.7, the same as -3, 1.7. And -1, 1, the same as 1, 1. So this is known as a reflection across the y-axis, because what you're looking at here is all these dots moving like that. If you imagine that the y-axis is a mirror, you're seeing exactly the same thing out here. There's a few caveats on this though, all right? The negative root x rule is only valid for values of x that are less than or equal to 0. As you can see from the table of values, when x becomes positive, so here, oops, not the 0, 1, 2, 3, 4, the rule now becomes undefined, because when I plug +1 into negative x, it becomes -1, and I'm not allowed to take the square root of a negative number. So this rule only works for values of x that are less than or equal to 0 in the first place. All right? It has the same shape as the original root x function, and it has the same transformations as. So the basic form is still a root minus x minus h, and I put the brackets there to show you the general form, because this is how you want to think of it, and I'll show you an example later on. So there has to be a negative underneath the root sign to show this reflection across the y-axis. All right, so a quick sketch question to do with the previous example of a reflection across the y-axis. We'll do that now. So first of all, we're going to draw a quick sketch just to get an idea of what it should look like when we're finished, and then we'll go through and solve. So looking at the equation, you've got yourself it here. You notice that it's got a k value of 3, but it's not written in the form that we're comfortable with here. So it's written as 2 minus x, and you might remember that the original form had to be like this, with a negative and then x minus h. So this 2 minus x, if I factorize out a negative sign, so if I divide everything by -1, what's going to happen is it's going to flip this sign here into a positive, so it'll become 2 plus x, and it's also going to put a negative in front of the -2. So it's going to be written, oops, going to be a better way to write it is x plus 2 with a -1 out the front. Now I'm looking at a very similar form to the general form we had at the start in the previous example. So I have this -1 here, I have a h value, and I have a k value. So this one here means reflection in the y-axis. This one here means 2, oh sorry, I made a mistake there. That should actually be a negative there, shouldn't it? Be to reflect their negative above here. All right, so this means 2 units right, and this one here means 3 units up, +3. So coming to do a quick sketch before we go and calculate any further, the original starting point was here. then it's been translated 2 right and 3 up. 1, 2, 3. So the new starting point is now here. Now, the original form looked like that. There's been no stretching, and it's going to look like this as well. All right, so that's a pretty poor sketch. But you can see that there's not going to be any x-intercepts, because it's too far up. There is going to be a y-intercept though, so we're going to have to solve for y. All right, so to solve for y, we set x equal to 0. So we've got -1, 0, -2 plus 3. Y equals the square root of -1, -2 plus 3, which is the same as the square root of 2 plus 3. And that point there is where we're going to leave it, because that is the most exact we can be. So we can see there that this point here we can just simply call 3 plus root 2. And we'll leave it like that. We'll call this point 2, 3, and we can put the arrow on the end and label the function. We'll label it y equals square root of 2 minus x plus 3. All right, so to recap, this, when the x underneath the square root sign is negative, it indicates a reflection in the y-axis, which normally looks like going out to the left, the very same as the one going to the right, but just the opposite direction. It acts in the same way. It has the same h values and k values, but you do have to rearrange it in case it hasn't been written. You have to rearrange it into x minus h. All right, you may not leave it like that and read transformations off it. From there, it's just a simple matter of making sure you do the calculations to find out the important points on the graph.